Hi everyone, my name is Zuozhi Wang. I'll be talking about Tempura, a general cost-based query optimizer framework for incremental data processing. Incremental computation is widely used in many scenarios. Each of these scenarios has its own unique requirements and characteristics. We will look at some of the common use cases and explain how incremental computation works. Let's look at the first scenario. Suppose an online shopping company has its sales data continuously ingested with an interval of every hour. The user wants to calculate the total income of the day over time. When the sales data at 1 a.m. arrives, we calculate its sum. At 2 a.m., we first calculate the sum on the newly arrived data. Then we need to combine the new sum result with the last result. The same process repeats for each hour until the final data arrives. In this scenario, we have a stream of input data arriving continuously, and the user is interested in the result of each incremental update. Let's look at another scenario in a data warehouse. The user wants to see an end-of-day report by transforming the sales data. Using traditional batch computation, we accumulate all sales data and compute the report at once. This chart shows the resource usage of this data warehouse. In the rush hour, many jobs are competing for resources. Incremental computation can be used to avoid the rush hour in the end. However, if we update the result, as soon as the new data arrives, some of the computation will still run in rush hours. One observation is the user does not care about the intermediate results. As long as we give the final result, we have the freedom to choose how to do incremental computation throughout the day. We can assign a cost factor for every hour based on the resource usage pattern, and it could be used by a query optimizer. For example, we can choose to skip the computation at 1 a.m. rush hour, then do more work at 2 a.m. when the resource usage is low. Let's look at another example of late data processing. Initially, we have most of our data ready. A small amount of late data will gradually arrive. The user is interested in the first partial query result and the final complete query result. In this query, the first operator can be incrementally computed with a very low overhead, such as aggregation. The second operator has a very high incremental computation overhead, such as outer joins. It is not worth it to compute the second operator for each small amount of late data. In this case, we can choose to incrementally compute only a subquery. For example, at 1 a.m., we only compute the first operator on the input data. We repeat the same process until the last data arrives, then we compute the final output result. These scenarios have their unique requirements and characteristics, but at core, they all use incremental computation. We want to build a unified query optimizer framework for various objectives, so optimizer can capture incremental computation in its most general form. We model the incremental computation problem as follows. First of all, we have a list of k time points. On each point, we have the set of available input data. The user specifies the expected result on each time point. The optimizer also has a cost function over time. The output of the optimizer is a list of physical execution plans to run at each time point. We have established the optimization objective of the framework. The next question is how to do incremental computation. This problem is also not trivial since there are actually many algorithms. However, no single algorithm is always optimal. We will look at two algorithms, retractable and non-retractable incremental computation. Suppose we have two tables, sales and returns. The sales table contains the profit for each order. The returns table contains the loss for each return order. In order to compute the gross income, we first do a left-outer drawing operation, then aggregate the result. Now let's see what happens if the orders table and the returns table arrives incrementally. We assume these tables are both up and down. At T1, the sales table arrives and no orders are returned yet. Then at T2, return order 01 arrives. We need to retract the old profit for 01 and update it with the new loss. At T3, the return order 02 arrives. Similarly, we need to retract and update 02. Finally, at T4, there's no more new data and we get the final result. In this algorithm, we need to retract the output whenever new return data arrives. Let's look at an alternative non-retractable algorithm which avoids any possible retractions. At T1, since all sales orders could be possibly returned in the future, there's no output data. At T2, return order O1 arrives. We know it will not be retracted, so we output the result. At T3, similarly, we output the results for O2. Finally, at T4, since there will be no more new data, this algorithm can safely output the result for O3. This non-retractable algorithm is more efficient when there are many return orders. However, if the return orders are rare, this algorithm will leave most of the computation in the end. Instead of letting users manually choose an algorithm to use, a cost-based optimizer can find the optimal algorithm from the statistics and the cost function. We have learned the complexity of incremental computation under many scenarios and with many algorithms. In this paper, we propose a new model for incremental computation. We also provide a rewriting rule framework that can describe many incremental computation algorithms. We also integrate Tempura with a volcano-style query optimizer framework. Now let's look at some technical details. The optimizer is based on the concept of time-varying relations, or TVR in short. TVR has two perspectives, snapshot and delta. A snapshot is what the table looks like at each time point, and a delta is the changes between two time points. Snapshot at T1 and the delta from T1 to T2 can be merged to generate the snapshot at T2. We introduce TVR as an extra data structure in the query optimizer. Each horizontal line represents the operators in a TVR. Initially, we have an operator tree of the original query. Suppose we have two time points. We first expand it into three operator trees for snapshots at T1, T2, and the delta from T1 to T2. Now the question is, how can we incrementally compute the join operator and the aggregation operator? The incremental computation algorithm for each relational operator have been well studied, and they can be included as TVR generating rules. For the left outer join operator, it needs to combine the last result with the new delta input. The rule is a little bit complex, but we can view as one operator. For the sum operator, the rule is to simply apply sum on the delta input again. After the delta from T1 to T2 can be computed, next we need to combine a snapshot with a delta using intra-TVR rules. For the left outer join operator, we add a union operator. For the aggregation operator, we first union the early results, then apply sum again. The inter-TVR rules specify how the results can be indirectly computed. It's more commonly used in advanced algorithms. The non-retractable algorithm decomposes the left outer join into a left anti-join, which contains retractions, and an inner join, which contains append-only results. This algorithm only incrementally computes the inner join. The inner join and the left anti-join has special relationships with the original left outer join. Their snapshots can always be merged using a union operator. If we repeatedly apply these TVR rules, we can get the full search space for this query. Any path that can reach the final output is a valid execution alternative. For example, this path shows the incremental execution of the retractable algorithm, and this path shows the incremental computation of the non-retractable algorithm. There are many more details of the optimizer in the paper, such as how to change the memo and the rule engine, how to speed up the optimization process. These details are available in the paper. Now let's look at some experiments. We implemented 4 algorithms, and Tempura can unify all of them. We tested 5 queries with 4 data arrival patterns and 2 cost functions. The experiment results shows that each individual algorithm is good at different scenarios, but for Tempura, we can always find the best plan. For query optimization speed, Tempura can finish the optimization of 80% of TPC-DS queries within 3 seconds. Although it's a little bit slower than traditional query optimizers, we can get a significant runtime saving. We open sourced the implementation of Tempura on top of Apache Calcite. The full source code is available on GitHub. We are also actively working with the community to contribute Tempura back to the Apache Calcite project. Thank you.